So that's one concept which I wanted to introduce. Yes.
So you were talking something. You mentioned something about in case the order goes up higher, you can still use this method to tell that it is still stable.
So means performance, right? So see what I mean is that, see, let's say you have a 10th order system, for example, right? So you need to design a closed loop control system which is of order 10, but still, like I can always say, look, I will specify performance in this manner. See, the reason is the following, right? So we have explicit expressions for specifying performance specifications for systems of order 1 and 2, and by and large the dominant dynamics is going to be that of that order, right? So consequently, I can essentially create regions like this, and if I am able to place all my poles in this region, I am done. Okay, we will double check this. Okay, obviously I would place the dominant pair as close to the imaginary axis as possible, right? Isn't it? Then only they will remain dominant. See, think about it. We will anyway we'll do all this design process. Okay, when we learn about root locus and do the design examples. See, when I am using maximum peak overshoot and settling time for an underdamped second order system, I am implicitly assuming that like my dominant poles are going to be a pair of complex conjugate poles, right, which should be the closest to the imaginary axis, right. So when I design, I should ensure that the dominant poles basically are complex conjugate and they are the closest to the imaginary axis. That's something which I should ensure, right. So by and large it works out that way. You can also have, like, yes, you can say, look, I don't want dominant complex conjugate poles, I will have my dominant poles on the negative real axis. Fine, you are still satisfying the performance requirements, but what will happen is that the system response will become sluggish. That's what will happen, okay, because like your rise time value will go up, correct? So as we discussed earlier, right? Yeah. Okay. So this is just what to say, I would say an engineering solution, right, to visualize a domain in the S-plane where you can place the closed loop poles. Okay, that's the application, right? Of course, if someone says, look, design a closed loop control system whose time constant is, let's say, less than 4 seconds, what will we do? The moment I say time constant, I am telling you that the dominant dynamics will be that of a first order system, and if time constant is 4 seconds, what should happen? What was the pole of a first order system? -1 by capital T, right, for a stable first order system. So if I want time constant of at most 4 seconds, 1 by capital T will be -1 by 4. So I want all my poles to be to the left of -0.25 line. Okay, so that's how we should visualize. Is it clear? So that's an alternative example, right? So if I want my performance specification, I am saying that, look, like I want a time constant of, let's say, less than 4 seconds, like then automatically we look at the step response of a stable first order system whose pole is at -1 by time constant. So time constant of at most 4 means my pole should be to the left of -0.25 line. That's it, right? So that will ensure that I satisfy that criteria. Okay, so those are the that's the way we construct, and then like we look at performance specifications. Okay, so one more thing which we are going to do today, at least start today, is analysis of steady state errors. Okay, so before we go, we put everything together and then like start doing controller design. So this is something which we are going to discuss today. Okay, so how do we analyze steady state errors? Because see, by and large, like we design controllers, like to do some let's say regulation or tracking, right, follow a desired behavior. See, for example, I would design the air conditioner in this room to meet a set temperature, right. So I will come and set the temperature as 25 degrees Celsius. I want my controller to maintain the temperature of air near 25 degrees Celsius, right. So obviously I would be happy if as time progresses I stay near 25 degrees Celsius, right, is it not? That's when I will tell that, like my system or controller is performing well, right. So steady state errors become very important, right. So and they become very critical, right. So, see, for example, I am developing an autonomous vehicle, right. I wanted to essentially follow a particular trajectory. I wanted to be an autonomous car which has to travel within a lane, right. So, I do not want the car to oscillate in that lane and also like deviate from the path, right. That is going to have serious implications, right. So, as time progresses, what is going to happen to that vehicle, right. So, that is something which we should figure out. So, let us look at steady state errors. So, how do we analyze steady state errors, like, so let us construct the standard closed loop negative feedback system that we have been looking at. So, and this is the feedback path transfer function, and this is the feedback diagram, right. So, please note what was G of S called, that is what is called as a forward path transfer function, right. H of S is the feedback path transfer function, right. So, recall that the closed loop transfer function is essentially equal to Y of S divided by R of S, and what was the expression for that? It was G of S divided by 1 plus G of S H of S, right. So, that was the expression for the closed loop transfer function, okay. So, we are going to essentially make an important assumption, okay. Let us assume that the closed loop system is stable, okay. So, of course, then only we can talk about steady state errors, right. Think about it, right. Let us say if I do not stabilize the closed loop system, there is no point in talking about steady state performance, right. So, let us assume that the closed loop system is stable, okay. So, that first requirement of stability, the critical requirement of stability has been met, right. That is an assumption we will make before we proceed, right. So, immediately we note that E of S divided by R of S is going to be equal to what? What is E of S by R of S? 1 divided by 1 plus G of S H of S, right. So, that is pretty obvious, right. So, because of course, you can say Y of S is G of S E of S. So, E of S is 1 by G of S times Y of S. So, you get this, or you could go the other way around also, right. So, you can pretty easily figure out that E of S by R of S is going to be 1 by G of S H of S. So, this implies that E of S is going to be equal to R of S divided by 1 plus G of S H of S, okay. So, what is the name that we associate to the function G of S multiplied by H of S? Open loop transfer function, right. So, G of S, let me write it down once, right. So, G of S is what is called as a forward path transfer function, right. H of S is what is called as a feedback path transfer function, right. So, G of S times H of S is what is called as a open loop transfer function. Please remember these terms, okay. Yeah. See, of course, in your quizzes and exams, I won't give a nice block diagram and then like give you expressions, right. I would say design a negative feedback system, like, and if I say unity, that means H of S is 1, right. I may say the plant transfer function is something, controller transfer function is something. So, then you should be able to figure out G of S and so on, right, correct. So, please remember these terms, right. So, this implies that the steady state error okay, let me call it as ESS, which is defined as limit t tending to infinity E of t. That is going to be equal to, if you recall, one of the properties of Laplace transform that we revised long ago, right. So, what was it? Final value theorem, right. So, that is going to be limit s tending to 0, s times E of S. So, this is going to be limit s tending to 0, s times r of s divided by 1 plus g of s h of s. Okay, so that is what we have for the steady state error. Okay. Now, let g of s times h of s be expressed as, let us say some b naught s power m plus b1 s power m minus 1, all the way till b m minus 1 s plus b1 bm divided by a naught s power n minus 1, sorry, s power n, sorry about that. So, the denominator is a naught s power n plus a1 s power n minus 1 plus all the way till a n minus 1 s plus a n. Okay, let us say we consider, right. So, let us say g of s h of s comes out to be in this generic form, right. Please note that I already have closed loop stability, I am reiterating that point again and again. Okay. Yeah. So, now let us say we can rewrite this as some k times, let us say b naught hat s power m plus b1 hat s power m minus 1 all the way till b m minus 1 hat s plus 1 divided by s power capital N, a naught hat s power, let us say k, let me not use the same alphabet, let us say we use p, right, plus a1 hat s power p minus 1 plus all the way till a hat p minus 1 s plus 1. Okay, let me tell you what I have done, right. So, what I am doing is that I am doing two things. First thing is that I am seeing whether there are some poles at the open loop poles at the origin. See, for example, what are open loop poles? They are the poles of the open loop transfer function, right. So, if I look at the denominator polynomial a naught s power n a plus a1 s power n minus 1 all the way till a n, if I have poles at the origin, then a n is 0 obviously, right. So, I can pull some s term out common. So, I can have one pole at the origin, two poles at the origin, three poles at the origin or none. Okay. So, the value of capital N can be from 0, 1, 2, 3 and so on, right. So, I am sure all of us agree, correct. Once I pull it out, what I do is that remaining factors also, what I am doing is that I am making the constant term as 1. I do some algebraic manipulation and then introduce a factor k such that the constant term becomes 1. We will see why, right, shortly, right. So, this is what is a general structure of the open loop transfer function. Okay. Now, when capital N is equal to 0, we call, for example, I am going to write 3 cases. Okay. So, when capital 1 is 0, sorry, capital N is 0, it is what is called as a type 0 system, okay, or a system of type 0. So, when capital 1 is, capital N is 1, it is called as a type 1 system and so on. You get the point, right. So, when capital N is 2, it is called as a type 2 system. So, a type 0 system does not have any poles at the, any open loop poles at the origin. Okay. Yes. Yes, yeah, they are different coefficients, right. That is why I am putting a hat over it, right. S power n common, but I am also dividing by bm and an, right. Is it not? Because I want to make the constants 1, right, and an may be 0 if I have capital N to be non-zero, right. So, I am just doing some algebraic operations, okay, I am just writing in a general form, okay. So, you will see why I am doing it, because I want the constants to be 0, but because in the two polynomials when I substitute s equals 0, because that is where I want, how I would use my final value theorem, right. I want to end up with just 1 and 1. So, consequently I am putting whatever that ratio which comes out as k, capital K, right, outside. Okay. So depending on the value of capital 1, we have type 0, type 1, type 2, type 3 and so on. Okay. And see, for example, if you use an integral control, controller, we automatically get a type 1 system. I am sure all of us agree, right. See, what is the transfer function of an integral controller? Ki divided by S. If you use Ki divided by S in our open loop transfer function, I automatically have a S in the open loop transfer function denominator, right. So I automatically get a type 1 system. I am just giving an example. Okay. So please remember this. Okay. So that's the terminology which we use. Did I make a mistake here? Yes, okay, what is P? Let me write it here. So n plus P is equal to small n, sorry. Okay, that order is preserved. Sorry about that. Okay, I forgot to write that. Okay, so I may have, see, for example, if capital N is 0, obviously P is equal to N. No, I don't do anything. I just divide by B, M and A N. That's all I do. Right?
Sir, what about the negative values of P?
Negative values of?
We'll have P minus N also, because we are taking S to the power N problem.
1 by S, wow. See, if I have a factor like S, okay, only if I am not factorizing, what to say, with any other number, right. So only if I have a root at 0, I am pulling it out, that's it. Other terms will remain like this. See, let me give an example, maybe let me try to convey it better. See, let's say, for example, let's say I had the denominator to be this, right. So plus 4s. What can I do? I can do this, right. Correct. Then what can I do? I can also do this. Okay, by 4 plus 3 by 4s plus 1. Am I correct? That's what I have done. Right? Did I do it correctly? No, this is 4, right? This should be, I am pulling out 4, right? Then I will get this. Correct? Yeah. Denominator. See, denominator, of course, I am assuming that there are no pole 0 cancellations at the origin, right? So I am assuming that there is no 0 at the origin. Okay? Yeah. Yes. AN should be 0. Yeah, agreed. Yeah. So for type, say type 1 and 2, 1 and higher, my original AN should have been 0, as you can see from here. Okay, I am only writing a pth order polynomial here, right. The only thing is that I am making the constant term of the pth order polynomial as 1. That's the only thing. Okay, yeah.
So I try to get a particular value for V cap and V0, V not cap, V1 cap. Purpose of taking K outside.
We will see. Yeah. So I preemptively told you why am I taking out. Let me once again do another example. Then we will. I think we'll stop here and then we'll continue. Right. Let me do an example. Right. So let's say I have s plus 4 divided by this s cube plus 3s plus, let's say I change the number. Right. So let's say 5s. Right. So what I do is that I take 4 out in the numerator. Right, I make it as 0.25s plus 1. Am I correct? Please stop me if I am making a mistake. And then I take 5s common in the denominator. I get 0.2 s square plus 3 by 5 is going to be 0.6. So this should be s squared. Sorry, 0.6s plus 1. Right. So what I do, what I have is that I have 0.8. Times 0.25 s plus 1 divided by s 0.2 times s plus 0.2 s square plus 0.6 s plus 1. Okay, that's how I read this polynomial. Okay. So here capital N is 1, small p is 2, right? M is 1. Okay. and Ka happens to be 0.8. Okay, and that's what is called as a open loop gain. Okay, like we will come there shortly next class.